So we're gonna let 2 minutes for everyone to join, and then we're gonna start. Okay, let's go. So today, everyone, we are on week 7, and as we have told you yesterday, we're going to talk about transformer today. And you will have your returning instructor, Dr. Parsa Bagherzadeh, which has extensive experience with transformers, so he's the perfect instructor for today. So just as a reminder, we are right now in phase 2 of the program. So right now we are seeing more advanced like models and architectures for medical problems. So right now we are in week 7. So it's almost the end of the workshop series. So we're going to see more technical stuff. So really don't hesitate if you have any questions. I'm going to introduce our mentors right after this slide, but feel free to ask in the chat if there is something you don't understand or you want the instructor to explain again. Feel free to do so. The idea is that you get out of this workshop with some knowledge. So yeah, feel free to communicate with us. So again, so yesterday we had the 2 speakers talking about medical decision transformers and also how to make AI accessible in resource-limited countries. And today we're going to have more extensive details about transformers. So I'm going to introduce our 2 mentors. I saw that Nicole is here today. So Nicole is an MD PhD student at McGill University. She loves all aspects of machine learning in medicine, and she's coming from both a medical and a machine learning background. So it has helped her gain a new perspective in the integration of the 2 fields. So she's the perfect like mentor for today as well. Her research focus is on GFlowNet and causal inference applied on cell trajectories. And previously, she worked in industry on developing therapeutics for rare disease using machine learning. So feel free to use your mentors as well. I'm just presenting them so that you know who is answering you your question on the chat or on the Discord, and you will have the opportunity to meet them also next week during the actual tutorial. And now, Shami is a recent graduate in machine learning from Mila and the University of Montreal in Canada. In April 2023, she became a Rising Star awardee by WOM X-Men in data science, and in November 2022 she was an awardee for WeaveSphere Developer 30 under 30 of Canada. In May of last year, she became a runner-up in the Outstanding in AI Young AI Role Model of the Year North America Award by Women in AI. Last year, she worked at Amazon Web Services Test Track team as a research engineer intern. Her work focused on model-based noisy annotation detection and correction. And previously, she was a machine learning engineer at fast-paced startup Shipments. She's passionate about tech and community, and her journey has led her to become an international speaker, one of the youngest Google developers expert in machine learning, and Google Cloud champion innovator around the globe. To date, she has spoken at 30+ conferences and have trained 20K+ professionals and students in machine learning, deep learning, TensorFlow, and Google Cloud platform. So you have a great instructor for today and 2 great mentors. So please make good use of them. Don't hesitate to communicate and ask questions as we're seeing more advanced topics. And now I'm going to present our amazing speaker for today, which is Dr. Parsa Bagherzadeh. For those who did not have the chance to attend his previous workshop, but actually if you didn't have the chance to attend, you can still watch the recording. But okay, so Parsa Bagherzadeh obtained his PhD in computer science from Concordia University under the supervision of Professor Sabine Bergler, and he was a proud member of the CLAC lab, Computational Linguistics at Concordia. In his PhD, he focused on the integration of external knowledge sources for language processing, specifically biomedical text processing. He has a master's in artificial intelligence from Ferdowsi University of Mashhad, Iran, and a bachelor's in computer science from the University of Virgin, Iran. Currently, he is a postdoctoral fellow at McGill University, where he focuses on natural language processing techniques to leverage clinical text reports for cancer treatment outcome prediction. So he basically uses transformers in a daily basis. So it's really the perfect instructor for you and for this workshop today. So please, Parsa, feel free to take it over and share your screen.
Thank you, Sebastian, for the introduction. Hello, everyone. Good morning to all of you that are living in North America. Good evening to everyone else that is living in Eastern Hemisphere. So, see my screen?
Yes.
Okay. So, let me go present a slideshow. So yes, hello again, as Sebastian mentioned, we're going to talk about transformers today. Transformers, they were originally introduced in 2017, and when they were introduced, they revolutionized mainly language processing, natural language processing, and then in 2021, they were extended to image processing. So we are going with a historical point of view first, and then if we move forward with the same order that they were applied. So let's first talk about context. When you are talking about context, context is a very important aspect in both natural language processing as well as image processing. Without considering the context and having something and trying to interpret something out of the context, one cannot have a good understanding or a reliable understanding of the phenomenon at hand. Okay, suppose you have a textual input like Lenvima is effective for the treatment of thyroid cancer. We had this sample and piece of text before in our previous session when I was talking about, for instance, dependency parsing. And so the question is how the meaning of a word should be represented. For instance, Lenvima, how we can have an understanding of Lenvima, right? So those of you that know about cancer, the thyroid cancer, and have some medical background, you know that, or pharmaceutical background, you know that Lenvima is a drug. However, without having external knowledge, how we can talk about the meaning of this word. So Firth, J.R. Firth, he has a very famous quote that you shall know a word by the company it keeps. It means that you can know about the meaning of a word by looking at the context that this word is appearing in. Okay, so for instance, what are the contexts for this Lenvima? Is treatment, is thyroid cancer, right? So these are the two most important or the three sort of most important terms that we have in the context of Lenvima. So we by looking at the context, we can infer that Lenvima is something that is used for treatment. So it should be a drug. Okay, so by looking at the context in a sentence, by looking at a context in an image, we can understand what is actually the object or the token, or the meaning of the object or the token. So, but how to capture this context, right? Because if we want to have a representation for a token, if we want to better present a token that actually takes into account the context, we need to somehow capture this context. So when I was talking about RNNs in the last in the previous session, we reviewed very quickly what is an RNN. RNN, instead of in contrast to feed-forward nets that only has one input, and it has an input as a one single time step. It has several inputs and a sequence of inputs. Okay. So it can process sequential inputs, and the output and the actual, when we're applying a recurrent layer over a sequential input, you're obtaining a hidden representation. These hidden representation, the hidden representation for instance, for this time step is a function of the previous hidden representation and the current input. Okay, so one can argue that this hidden representation H1 has the information of all of these tokens, all of these inputs that has been seen so far, right? For instance, H2, again, we can argue that this is a representation of X1, X2, right? For instance, it's a representation of Lenvima is. Lenvima is. And until the end. Okay, so in general, HT is basically a representation of the sequence up to that position. So it's a representation of the context that has appeared in the sequence until up to that position. So we can argue that it represents some context. Okay. However, why I'm saying some context, because it is not aware of the future tokens, right? So here, when I provided this example to have an understanding of Lenvima, okay, we need to see what is coming at the end, the treatment and the thyroid cancer. So when you are processing the Lenvima as a token at the first position, and you are getting a representation for that token, or for what we had so far, we are not looking at to the future. We are not looking at the subsequent tokens. So that's why I'm saying it represents some context and it's not bidirectional. So there is a solution to this, to have actually two recurrent layers, one that is scanning the sequence from left to right and one from right to left, and then somehow combine the corresponding hidden representations. Okay. However, again, this is not a good answer and a good solution to this challenge, to this problem that RNNs they really cannot capture the context well. Also, for when we are talking about context, CNNs also as neural layers that are able to process see both sequences and for instance images. It also captures some context, right? So again, we are assuming that we are convoluting and we are convolving actually a window, a filter over our input. The input might be an image or a text here, again, because this is more familiar. I took this from the previous set of slides. We are sliding this filter over this input, right? So actually, we are assuming a window for the context. Here, the window, the size of my window that captures this context is 2. It's capturing bigrams, right? It captures 2 consecutive tokens. So again, it captures some input, okay, but the context is still limited, and we are actually representing each token by its adjacent tokens, okay. And another problem for CNN is that it does not well capture the spatial information. What do I mean? If you run a CNN over this face and try to classify it, so it says, okay, this belongs to the class of face. However, if you also apply this apply the same CNN over this shape that I have no idea what is it, it again says it's a face. Okay, so a CNN fails to well distinguish to have a good distinction between these two images. Okay, this has to do with many of the limitations that CNN has, that makes it not suitable for advanced image processing. So Again, because the context that that CNN is looking at is a very local context. It's a very limited context. Okay. However, for many image processing applications, we need to go beyond the local context and actually look at different places and different locations in an image. So, what are the solutions to this? So the context actually needs to be adaptively determined, not necessarily the tokens or the patches or the areas in the image that are close or adjacent to what we are and where we are, and not adjacent to the current token, for instance. But sometimes we might need to actually attend and have more attention to tokens that are not adjacent to the current token. And also bidirectionality, specifically in natural language processing, is a must. So we need to come up with a solution that have an adaptive context and also looks at all of the tokens at the same time, not tokens one by one like we had in RNN, and also have different attention to different tokens. Depending on the input, it needs to adaptively look at different parts of the input. So let's talk about attention, because I just said that it needs to have different attentions and attention to different parts of the input. So what is actually attention? So let's first talk about dot product attention, which is a general form. So the attention mechanism is actually a function. It's actually a function that accepts three arguments. One argument is what we call it query, key, and value. Okay, so the attention mechanism of this dot product attention mechanism is a general form. We also have other types of attention, but the most common form is this dot product attention mechanism. So the attention mechanism actually maps a query, okay, a query and a set of key value pairs. So when I'm saying key value pairs, it means that there needs to be some kind of a coupling between this key and value. And I will tell you what does this coupling mean. So it maps a query and a set of key values to an input. So how it basically calculates the dot product between the query and the transpose of the key. Then we optionally we have a normalizing factor here that rescales our input. Nevertheless, this is not important at the moment. Then the results, we are taking a softmax over this. Why? Because we want to actually compute a weighted sum of these values. So let's talk about what does this query, key, and value mean. So query, key, and value, they are matrices. Okay, so query here is a matrix, it's a transpose of a matrix, and value is also a matrix. So if you look at these, so each of these matrices, they have different number of rows. For instance, this matrix has a row. Each of these rows, we can assume it as an object, as a representation for an object, as a representation for something that we want to attend to, or something that wants to attend to something else. Okay, so a query, key, and value, if I want to put it simple, query is something that wants to attend to something else. Okay, again, query is something that wants to attend to something else. So if we go back, for instance, here, if we want to represent Lenvima, we want this Lenvima to attend to, for instance, to treatment or thyroid cancer, okay? So this Lenvima would be a row, the corresponding the word embedding for Lenvima that we talked. So for instance, in the previous session, we talked about word embeddings. the word embedding for that lengvima would be a row, right? A row in this query. So anything that wants to attend to other representations would be a row in a query. Okay, and the key and value, they are objects or the entities or the representations that other entities are attending to, right? Again, if I go back, treatment and thyroid cancer, lengvima wants to attend to these entities. So if we want to let this happen, we need to include the representation for the corresponding tokens as rows in key and value. So again, query is something that wants to attend to something else, okay? And the key and value, the rows in key and value, there are object or representations that we want to attend to, okay? So actually, when we are actually multiplying this query and key transpose, so we are multiplying this row by this column, right? So suppose this is the representation for lengvima, okay? And suppose this is a representation for what? For instance, for cancer, okay? So we are multiplying the representation of lengvima and cancer, okay? So this row by this column. The results would be aggregated here. This would be the result. So then we are again multiplying this row by this column. The results would be here. Okay, this row by this column. The results would be here. Okay, so when we are actually calculating the dot product, because we are calculating the dot product of this row and this column, dot product, always remember that dot product, in some sense, it measures the similarity between what? Between two objects or two vectors. Okay, so when we're actually calculating this product, we're actually calculating the similarity of each of these entities together. So this row by this column, the similarity would be here. And then we calculate the softmax, row level softmax. So the summation of all of these values, would be 1. So what would be the result and what would be the outcome when we are multiplying the output of the softmax by the value? So we are multiplying this row by this column, again this row by this column, and we are actually taking a weighted average. We are calculating a weighted average of the values and the entities that are provided as our values, okay, as something that we want to attend to. And if you look at this, my key and my value, they have so the key actually had 3 rows and key transpose now has 3 columns. So we had 3 rows in key, we had 3 rows in value. That's why I said key value pairs, and there is a coupling between this, right? And if you look at this, we have the same number of rows as we had in query. That makes sense because we had, for instance, 2 sets of representation or 2 set of objects or 2 tokens that wanted to attend to other objects. Okay, suppose here we had provided only lengvima and is. Okay, so lengvima and is we provided as query. And for instance, we provided treatment of thyroid, treatment of thyroid as key and value. Okay, so what we actually did is actually we obtained a new representation. We obtained a new representation for lengvima and is based on the attention or based on looking at the query and the key and value. Okay. So the objective of basically attention mechanism is to provide, to obtain a new representation for our query by attending to key and value. So depending on what are these actually query, key, and value, the behavior of this attention mechanism would be different. Okay, so if we provide and we set query key and value equal to the actual input matrix or input embedding that we had. Okay, this X is the a matrix of all of the for instance word embeddings that we had as input. Okay, if we do this, we have self-attention. Why we are calling it self-attention? Because if you remember, I said query is something that wants to attend to other things. Okay, wants to look at other things, and query and key and value are objects or are the representations that we want to attend it to. So actually, we are attending to ourselves, right? This X is attending to itself. So, and so we are formalizing it like this: attention of XXX, which is the softmax of XX transpose, okay, times X. Okay, so this way we are actually obtaining contextualized representations for each token, right? Because here I mentioned that we have obtained a new representation for this query based on what we have as key and value. Here we have obtained the output of this would be a new representations for the rows in this X, which is also our query, based on other tokens by looking at the other tokens. So in self-attention, actually each token is represented using other token and also itself. Because why? Because we also have that token in X. So in this, so here the output of the softmax here, it was a 2x3 matrix. However, in self-attention, we always have a square matrix. Okay, so for instance, here if we have 15 tokens, we have a 15x15 matrix, and each of these entries would be the weight that we are putting for obtaining a representation for this token. For instance, for obtaining a new representation for token 0 at acquisition 0, we are putting this much on token 0 itself, this much on token 1, this much on token 2, and so on and so forth. So here I've actually looked at the the output of this softmax, and the output of this softmax when I visualize it, it's always the diagonal has always the largest values. Here we can see that it has it's almost 1 on the diagonal, and the results and the consequence of this observation is that a token always attends to itself. So basically, a token to obtain a representation for token 0, we are looking at token 0. Okay, so we are not actually looking at other tokens. So and we have something that I'm calling it trivial attention weights, right? We are always looking at the token itself. So why this has happened, and why we always have the largest values on the diagonal? It's very obvious. Why? Because when you are multiplying a vector, when you are calculating the dot product of a vector by itself, it always has the largest value. When the dot product of two things has the largest value, when the two things are the same. Okay. So actually, this is a failure. Why? Because we as I mentioned before, we need to adaptively learn where to put more weights. For instance, to obtain the representation for this token 0, we might need to look at the token 0 itself, and maybe more to token 12, and a little bit to tokens, for instance, 7. But right now, it's always largest value on diagonal. So what is the solution and how we can fix it? In practice, although we are mentioning that the attention is x, but we are using some linear transformations like WQ WK and WV for constructing actually these query key and value. So it means that before doing this multiplication, we are projecting X to the same space, or we can project it to another space, and we are projecting this this X again to another space. We are making it we are changing the representation. We are this W, these W's are learnable parameters and trainable parameters of the model. By this technique and by this solution, we are actually can avoid trivial waste that we had in attention mechanism. Why? Because now it's now we can consider this as X tiled or X prime. This as and this we can consider this as X prime prime. So the two matrices now they are not the same. Okay, then we won't have trivial attention weights. If we visualize this piece, the output of this softmax, you would have something like this. In this case, you can see that, for instance, here for token 15, we are putting more weight on token number 2, and again more weight on token number 4, and a little bit on token number 0, and apparently nothing on token number 14. Okay, so by having this trainable parameters, we can avoid this, and we can actually train the model and guide the model to actually look at different contexts and look different tokens. Okay, but the question is, what if the context is not important? Because there are certain tasks that you don't need the context to actually make a prediction. What if the context is not important and you don't need to look at other tokens, okay, and other places and other positions in the input? The thing that you can do is basically if that's the case, these linear transformations would be trained to characterize the identity function. So the optimizer and the training process would guide and lead these trainable parameters to capture the identity function. So in that case, X, it would be X transpose, and again X. So and the context would be ignored. So, but by adding these linear transformations, we're actually adding more degree of freedom and more learning capacity to our model to actually look at different parts. Now that comes the transformer. So the transformer architecture is an attention-based architecture that uses self-attention. Okay, so we use the dot product attention as the building block. However, we are providing the same input as key query key and value. Okay, so this dot product attention actually obtains contextual representation. Then we have to avoid exploding gradients. We are adding or vanishing gradients. We are adding a residual connection here. Then to do more learning, to add more learning capacity to our model, we have a feed-forward layer, and it would provide an output. So one thing that is really important is that RNNs. When we talked about RNNs, the RNNs process their sequence one token at a time. So each hidden representation at each time step actually corresponds to a position. So RNNs inherently they capture the order and the order of the tokens. However, when we are calculating the attention mechanism here, when we are averaging over these and we are mixing these different entities, we are actually throwing away the order information. Here we have some sort of order in this matrix, but when we are taking the average here, when we are multiplying, when we are taking a weighted sum of these values, you're actually throwing the positional information out. So The solution is to add some sort of positional encoding to the original input before passing it through the attention, through the transformer layer. Okay, so we have the original input. This positional encoding that I'm going to talk about in the next slide would capture the order of the token. Okay, it captures the order, and then when you are passing it through the self-attention mechanism and the rest of this block, they know about the order in which the tokens are appearing. Okay, so this is a transformer architecture. This is not something very complicated. This is the backbone of BERT, which is one of the revolutionary language model to introduced in 2019, and then all of its variants and all of the other things that use this transformer as the backbone. For instance, GPT-1, GPT-2, GPT-3. So we know about GPT-1 and GPT-2. We don't know about the architecture of GPT-3 and so on. But both 1 and 2, they used some sort of a transformer as the backbone. So now let's talk about the positional encoding. So again, it was used to capture the absolute position of the token. So to capture that, okay, this token is as position 1, this token is as position 2, 3, so on. Okay, so this positional encoding is actually in the same shape as our input. If our input has a capital T tokens, or it has capital T representation stacked on top of one another in a matrix, the positional encoding would be of the same shape, okay? Because we want to add each row, the corresponding row, and accumulate this corresponding rows, okay? Add x1 to for instance, P1, that's the first row in this positional encoding. So it should have the same shape, okay? So this positional encoding either is randomly initialized and learned during the training process, or we can use some sort of constant embedding, which is based on, for instance, based on different sine and cosine function of different frequencies. Okay, so both of these positional encoding are possible, but to have a better understanding of positional encoding and how it captures the order, I'm focusing on the constant encoding that is based on sine and cosine of functions of different frequencies. So here we are actually trying to fill out. We are trying to actually fill out a matrix. Okay. Here again, we had the capital T rows. Okay. We want to have a matrix that has capital T rows as well. Here, for instance, 15. Before I had 15 rows here, right? When I provided this X, here I had 15 rows. Okay. Here I'm also constructing a matrix of 15 rows with this formula. So what does this formula says? It says at this position, so to fill in the entry, this entry, for instance, we are starting at what? We are starting at 0 and 0. Here we are starting it here. In order to fill in this entry, use this formula. So when you are filling the even entries, use this one, and when you are filling the odd entries, use the cosine based function. So based on the dimension that we are working with, based on the original dimension of word embeddings, right? Because these x's they have a specific dimension, right? Based on this dimension of these word embeddings, so if you are providing word embeddings in 100 dimensions, like what I had for instance, was using glove embedding in the previous lecture. We are setting, we are constructing this embedding matrix. Okay, this embedding, this positional encoding has 15 rows and 100 columns, and we have filled it like this. If you look at the visualization of these rows, you can see that adjacent tokens, they have similar, relatively similar encoding. Okay, so for instance, the encoding of 0 compared to 14 is a lot different, but 14 compared to 13 is very similar. 13 to 12 is very similar. Okay, so the adjacent tokens, they have similar encoding, and that is actually makes sense, because the tokens that are adjacent to another token, the tokens that are falling in a window adjacent to a token, they actually they constitute the context for that token, and we have started talking about talking about the context. Okay, so nevertheless, it's not always the case that the adjacent tokens are the most important. However, this positional encoding somehow implicitly assumes that. Okay, if we take the dot product or cosine similarity between the representation of each of these positional encoding, each of these rows, we can see that so the dot product or cosine similarity. So this is the dot product. The dot product of 0 and 0 is the highest value. 0 and 1 is a little bit smaller, and then as we go further and as we get further to the sequence, and the tokens are farther, you're actually seeing that the distance is getting the similarity is actually getting smaller. Okay, we have less similarity. Now let's talk about BERT. So what is BERT? So we know what is a transformer. The transformer is actually consists of a self-attention layer, a feed-forward layer, and together with the input representation, we have the positional encoding. So let's talk about BERT. BERT is a transformer-based language model. It comprises 12. So the smallest version of BERT, so which is BERT-based, it comprises at least 12 stacked transformers. So 12 of these are stacked on top of one another, but only in the first layer we are providing positional encoding. So we're providing positional encoding, and then this hidden representation is directly fed into another layer of transformer. So it comprises at least 12 stacked transformers, and it's an unsupervised. It involves an unsupervised pre-training. How? We're providing an input to this transformer stack, and then we are assuming two main tasks. One is mask language modeling, and the other one is next sentence prediction. So mask language modeling is actually somebody has their microphone.
Yeah, don't worry. It's okay.
Okay. We are considering two tasks. We have mask language modeling, and we have a next sentence prediction. So mask language modeling, we are masking the input tokens randomly. So based on this context and based on the representation that is provided in the at the output of this transformer stack, we are actually predicting what was the token that was provided to me. Okay, what was the token that was in this, that is supposed to be in this position, which is eating. Okay, and the other one. So this was basically we are making a supervision here. We are training a classifier at this position to predict what was the mask token here, and we have the next sentence prediction. We are providing two sentences in the pre-training phase. We are providing two sentences in the input, And then we are classifying a representation, the representation corresponding to a special token, which is called the CLS token, to whether this sentence, "It's my favorite food," is supposed to come after this sentence or not. Okay, so and this is positive. It should be a positive classification, because yes, "It's my favorite food" is coming after this sentence. So it involves two pre-training tasks: masked language modeling and next sentence prediction. And why it is unsupervised? Because we are not putting any effort to make any gold labels for this, because we are pre-training these pre-trained language models on large corpora like Wikipedia and book corpus. And already we know that what are the tokens. We can mask a token and expect to have that token as the label that we want to predict. And we know that what is coming as the next sentence in a piece of text, because we know what is a natural language processing pipeline. It involves sentence splitting. We work with different sentences in the previous tutorial, so we can split the sentences and expect to classify it for the next sentence. So here compared to the ordinary transformer, that it involved only token embedding, that X matrix, and positional encoding, that P matrix that I showed in the transformer slide, we also have another sort of embedding that is added the same way that we added this positional encoding and the token embedding together, and then we fed it to the transformer stack. We are also including another embedding, which is segment embedding, which is basically captures the span of these two sentences, because it involves a next sentence prediction task. We ought to be able to actually represent the span of different sentences. So we are representing it by learnable embeddings like SA. So this is a vector. All of the tokens that are in the first sentence, they are being added with this embedding SA, sentence A, and all of the other tokens that are in the span of the second sentence are added with SB. So the point is, not all of these transformer-based models, they have segment embedding. Why? Because some of these, they don't involve a next sentence prediction task. For instance, Roberta, it's one of the very famous language models. Roberta does not have a next sentence prediction task, so it doesn't have segment embedding. Now, let's get to the good part. We have vision transformer. So it's really funny because CNNs, they were first proposed for image data, and then the NLP community took CNN and they applied it to text. And actually, NLP community saw text as some sort of an image, okay, and then applied CNN over it. But as a matter of fact, in 2021, it was the vision and image processing community that saw image as a sequence. Okay, this time it was the other way around. So, and they because transformers, they had a fantastic success in natural language processing and in NLP. They said, okay, let's try it and let's have a vision transformer. So in vision transformer, an image is seen as a sequence of patches. This image is patched, and then we are considering this image as a sequence of patches, a sequence like this. One can argue that this image is a sequence that goes like this, right? So we have a sequence of here. We have a sequence of nine patches here. Okay. Then we can assume that, okay, each of these patches are just tokens. They are token representation. They pass it into a transformer encoder, and then, for instance, do a classification for based on what we have here. Do pre-trained models. The same way that we have pre-trained language model, we can have pre-trained vision model. And it's the distinction compared to CNN is that it better captures the spatial information and spatial features. So, for instance, a vision transformer is better in distinguishing patterns like this compared to this. So it would say, no, this is not a face, but this is a face. Why? Because it holds vision transformer actually holds the position of each of these patches. So if you move this patch, the same patch that has the same pixel values to here, now the position of that patch, the positional encoding of that patch would be significantly different, right? If you move a token from this position to this position, the positional encoding would be very different. It doesn't matter that the token is for instance Lenvima. If you take the Lenvima from this position to this position, yes, the token embedding for Lenvima would be the same, but the positional encoding won't be the same. Okay, so that's why vision transformers, they better capture the spatial features and the positional features compared to CNNs. And now let's implement. So any questions so far? So Sebastian and Eugene, if
I don't see any questions on the chat, but feel free to unmute or ask questions in the chat if you have some.
So I can wait for a minute, and then I can go to the so let me just first share this link again with everyone. The link that I made for my notebook. So can everyone check that they have access to the?
Yeah, we have access. That's perfect.
Okay, so let's talk about the implementation and see that the implementation of transformer is not really that hard, and we can easily implement transformers. So this is my notebook for the implementation of transformers. So if you want to look at the paper that first introduced the attention and the transformer, you need to look at this paper. Attention is all you need. So which talks about the transformer model. Actually, transformer model has two parts. It has an encoder, this left part, and decoder right part. But for our purpose today, we are only interested in the transformer encoder, this part that I talked about. You have the input, you have positional encoding, and then you have the stack. So let's first implement the dot product attention. So I'm making a class for this dot product attention. So if you remember, if I said you need 3 set of linear projections to avoid trivial weights, trivial attention scores, and trivial attention weights. We need 3 set of linear projections. Here I have a query layer, key layer, and value layer. This is the only thing these are the only learnable parameters that you need for your attention mechanism. Okay, these are linear layers, and so the first one is projecting its input, which is usually in the D of model, into a query space, and the next one into a key space, and the next one into a value space. Okay, so it means that the size of these query key and values, they can be different. However, note that the query size and the key size, they needs to be the same, because we want to make that matrix multiplication compatible. If they are not, that query key transpose, if these two are not the same, they wouldn't be compatible. Sorry. So, but value layer agnostic, can the value size can be agnostic of what is the size of query and key. However, for our purpose, I'm considering all of these as the same as D of model. So this is basically the initialization of this attention class. What is the forward function? If you remember that the attention mechanism accepts 3 arguments: query, key, and value. First, I'm constructing query, key, and value. I'm passing the query into the query layer. It provides a query. Then it provides a key. So a key to the key layer, and the V to the value layer, it provides a value. Okay. Now I'm doing torch.matmul. I'm doing a matrix multiplication, query, and key transpose. So it's basically the same as what I had in the formula. The multiplication here. Then I'm taking a softmax. I'm taking a row level softmax. Okay. Remember, it was row level softmax. That's why I'm putting the dimension equal to 1 here. And then what do I have here? I'm multiplying that attention scores that I had with the value, and I'm returning the result. Okay, so I'm returning the result, which is the multiplication of the attention score and the value, and the attention score that I had from the beginning. Okay, so now I have a dot product attention here. I made a generic class for dot product attention. We can make an instance of this class. We can have a self-attention. That's then self-attention. I'm setting the D of model, query size, key size, and the value size as all of it as was 100. Okay, I'm making an attention layer. I'm having a random input here just for the sake of experiment. So it basically represents a sequence of 20 representations. Each of these representations, there are 100 dimensions. They are in 100 dimensions. Now to this self-attention, I'm providing as query, key, and value the same input, XXX, right? So let's first compile this part. So I'm importing torch as n and torch as always, and I'm also importing seaborn for my visualization purposes. Now let's run this, and let's look at the heat map and the shape of output. The shape of output is 2 times 100. Okay, the same shape as the input. So the self-attention, because we are giving this input as the query. Remember, I mentioned that in the output you would have the same number of rows as the query. Okay, so I had 20 rows in the input, and then I have 20 rows also in the output. And this is again a square matrix. See, this is a square matrix, 20 rows and 20 columns. Again, each of these entries, they represent the amount of weight and the amount of attention that we are putting on other tokens when representing this token. For instance, when we are representing token number 9, we are putting zero attention on token number 0, almost 0 on token number, for instance, 1, and more, for instance, more attention on 7, 8, 9, 10, 11, and so on. Okay, so, and the diagonal, again, the diagonal represents the amount of attention that we are putting on the token itself for representing the same token. Okay, so this is self-attention. Now let's have a class of positional encoding. Okay, so for positional encoding, we need for this encoding, we need basically a matrix of several rows, and the number of columns will be the D of model. Okay, we can have a maximum length of this, but in practice we can assume that this is unlimited. Okay, and we can have any length that we want, but overall we are considering a max length for our sequence. Okay, so basically the thing that we have this we are filling in a matrix, we are filling an encoding matrix, right? The even rows, the even columns basically they're filled by this, and the odd columns they're filled by this. Okay, and then we have our encoding. So, and for the forward pass, when we are providing an input to this position encoding layer, it only adds that input to the position encoding and basically returns the output. Okay, so the same way that is intended for a transformer. We need to add the position the token embedding to the positional encoding, and then pass it through the transformer layer. So let's have a positional encoding layer where the D of model is 100 and the max length is 512. Okay, and then let's look at the heat map and visualize the positional encoding. Okay, so here I have a positional encoding, and this is what this positional encoding looks like for 500 tokens and 500 positions. Okay, and 100 dimensions. I can have 200 as my dimensions. So it would be something like this. Again, as you can see, as you're going farther, these representations, the positional encoding for 0 is not much similar to 500, but this 500, for instance, is very similar to 480, so on and so forth. Okay, so depending, and you can have it, for instance, in 50 dimensions. It doesn't matter. The positional encoding has a general formula that takes into account the size of the embedding. Even in 10 dimensions, I can have something like this. This would be the positional encoding. But I'm using the 100 nevertheless. So, and that was the positional encoding, and having understanding of the positional encoding, then we can, now that we have defined the self-attention and attention mechanism, and then we have defined the positional encoding, we can have a transformer encoder. Okay, this transformer encoder inside has a positional encoding and a self-attention layer and a feed-forward layer, right? The feed-forward layer, we have it in the original transformer architecture to have more representation learning. So, and then the only thing that I'm providing to this transformer encoder model is the D of model, or the hidden size of these representations that are provided to the model, and the maximum length. Here again, I can change the max length depending on the complexity of my problem, on many aspects that are involved in a problem. So I'm making an object of this transformer encoder. Again, I'm having a random input. So for instance, only 25 tokens, or 25 positions, 25 rows. Okay. Then first I'm looking at the input shape. Then I'm giving this input to my model. I'm having a model output, and I'm also looking at the shape of the output. Okay. So the input shape and the output shape are the same. Because why? Because the transformer uses a self-attention mechanism. Self-attention has a query component. The same number of query the same number of rows that I have in my query, which is here 25, because I'm passing the input to this self-attention, right? The same I would have an output. Okay. So this is a very lightweight implementation of a transformer encoder layer. Okay. Now let's work with vision transformers and actually work with the Hugging Face library. Hugging Face library is a very popular Python and PyTorch based library for transformers. So it first started with transformers for NLP, but in the past 2 years, it has been extended to also accommodate vision transformers and other stuff. So first, we would install this Hugging Face transformers library by this pip install transformers, and I also want to use a database that is also provided by Hugging Face. I would install this datasets library, and then I would import the transformer. So by default, this datasets and this transformers library, they are not installed on Colab. You have to install it on your runtime. So while this is getting installed, then it imports the transformer. Then we want to work with a database and dataset. Let's look at this dataset. This dataset is a dataset that for chest X-ray classification. The objective is to basically to classify X-rays that corresponds to normal condition or pneumonia. So this data set in its training part, it includes 4,077 samples. Most of the samples in this database are normal or are negative, basically, are class 0. But there are also a fair amount of positive samples that corresponds to pneumonia. So nevertheless, so I'm from transformers. So I'm loading this database from datasets, load dataset. Then I'm loading that dataset. This is the address of dataset. You can also load other type of datasets and play around with these datasets. But for the transformer part, because transformers, the transformers library already includes a vision transformer model, already includes an implementation of this vision transformer model, and already provides us with image preprocessors that basically divides the image into patches, and then it turns these patches to the sequences, and it provides many good utilities such that we don't need to do it ourselves. Okay, so I'm importing from the transformer. I'm importing the auto image processor and also vision transformer model and the database that I want to work with. And once I loaded this database, I'm going to look at the training portion, look at the first sample, and look at the image actually. So this is the image of that. This is the first image that in this data set. It corresponds to a normal chest scan. Okay. Now let's go to let's define a class. Let's define a class: vision transformer classification. Vision transformer classification. I'm having an image processor, an instance of image processor which does the pre-processing for me. With which model name? Okay, let me just replace this model name with this because I want to make it parametric. So because we want to use a pre-trained model, a pre-trained vision model that is basically provided by Google. We are loading it from pre-trained. So this image preprocessor, we are using a pre-trained model. We would provide the name of that model later, but we would initialize an image preprocessor and a vision pre-trained model. Okay, here, vision pre-trained model dot from pre-trained. So we are loading the pre-trained weight of that architecture. And then we would have a classifier that basically projects representation from 768, this vision transformer. Basically all of the, it works in the dimensionality of this model is 768. Based on the specification and the config of your pre-trained model, you can change it to whatever that is that works for you. The forward pass of this includes the passing the image, passing this image to the image preprocessor, getting the image, getting the output, the output of pixel values as tensor, right, as PyTorch tensors, and then because I want to speed up my process, converting that tensor to CUDA tensor. Now this input is in. Now this input is a patchified sequence. So it's a sequence of patches. Okay, it's a sequence of patches. Here you can see that. No, so this you can see that hold on a second. Here I can print the shape of the output. The shape here just for you to see it. So the shape print input dot shape. Okay, there we can look at it. What is the shape here? And then when we have the signals of patches, we are passing it through that pre-trained model. We are getting a set of outputs. We are getting the last hidden state, the last the representation of the last layer of this transformer stack. Because just like BERT that comprises of for instance 12 transformer stack, this vision transformers also use a stack of transformers. We are interested in looking at the last hidden representation or the last layer. Then we took a mean pooling of these last hidden states. You can use max pooling, the pooling of your choice. It doesn't matter. Then I have a vector representation of this, my image, which is pooled, I'm calling it pooled hidden, passing through the classifier, and then doing the classification. So let's run this and compile this one. It basically, here I have provided the name of a pre-trained model that I want, Google VIT base patch 16.224, so on and so forth. Okay, so the name of these models are available for download from Hugging Face. We can browse different vision transformer based models and use different models. So because I want to iterate over this training set, I'm making a list out of this training set, the training part of that database. Okay. The loading of that database, it takes a little bit, and then I'm shuffling that database, okay? Because I want to shuffle the samples and have a mix of all of the positive and negative samples. Here I'm importing the Atom optimizer as my optimizer of choice. Then I'm passing the model's parameters together with the learning rate to this optimizer. I'm making an instance of a loss function, cross entropy loss. Then for 3 epochs, I'm iterating over the samples. I'm passing the image. I'm passing the image to the model. I'm getting a prediction and having a label. Here, calculating the loss.backward, optimizer.step. This should be very familiar for you. This training loop. Then having all of these loss values here as in this list, and then taking the average of all of these loss values. Okay. So. But I would run this only for few samples because I want you to see the shape of this input. Then I would remove this and recompile this. Okay, so let's run this. It's not a very good. So you see that this is the shape of my input. My input has a shape like this. Okay. But let me just so you can actually look at different look at different shapes that you have throughout your model. and basically inspect different parts of this this model. Okay. Nevertheless, I got rid of that input shape because I want to have a clean training part. Let's import this database again, and really this time train the model for real. Oh, my session crashed. No problem. Let me, because the size of the data set is a big size. So let me just import quickly whatever that I had from the beginning, torch.nn. Then let's again install this transformer. It quickly installs the library. Oh yes, this is a problem of working with free services, that sometimes you have limitations on your resources. Nevertheless, it works perfectly. So let's again run this, import this database.
Parsa, is it correct for me to say that participants need to activate the GPU runtime to run this notebook?
So yes, yes. Actually, here I have it activated. The GPU runtime is here. The GPU accelerator is activated. Okay. So yes, but right now I'm using a GPU. Here I'm using a GPU. I note that I have converted my model here, and this input, this process input to CUDA tensor. Okay, so it would use a GPU. But so the main part that we are dealing with is loading of this database, because this database is a database of 4,000 images. It's a little bit large, and that you can see it. You can see it in our RAM consumption, right? Here we are using 5 gigabytes of RAM. Okay, and it's going higher, but it's enough for our purpose. Okay. And right now we are not using any GPUs at the moment, except what we had in what we have converted to CUDA here. Okay, now 8 gigabytes. We are using 8 gigabytes of our resource, our RAM resource. So let's train this model. I'm training this model only for 3 parts, only for the first 200 samples, because I wanted to have a quick training. Okay. So because you are using a GPU, it's going faster. But it should be manageable with an ordinary CPU also. It doesn't matter if you use a CPU. It would run with a decent speed. So the average loss for first epoch is 0.49. I'm expecting the loss to go down for the next epoch. Yes, it went down. Right now I'm only training the model for 3 epochs. I can again continue the training, for instance, and run this cell block one more time and have it for another 3 epochs. But right now I want to look at the result of this 3 epochs. Okay. Now, so here, because the training set was big, I'm deleting and I'm freeing up the space for the training set, and then I'm loading the test set. Okay, and the test set again, I'm looking at the first 200 samples again to evaluate my model. So we are loading the test set. It would run much faster because we are not backpropagating any loss or so. So you see, even with 3 epochs, we are getting a final score of 58 for the one class, for class that represents our positive class. And if you continue the training process, you would definitely get better performances here. But you can do that yourself. So that basically concludes my part of the presentation.
That's perfect. Thank you so much, Parsa. So now we're gonna open the floor for questions. So feel free to either unmute or raise hand or put a question on the chat. So I might start with a question to get people started. So you talked about two ways, I think, to have positional encoding, Parsa. You talked about a constant way with like the
Sine and cosine.
and sinus, yeah, and also like a learnable way.
Yeah.
What is the most common approach, and what is done when you load, for example, like a pre-trained model?
So actually, different pre-trained models are using different schema for this. For instance, if you look at BERT, if you look at the actual BERT implementation, the language model uses a learned positional encoding. It is randomly initialized. It does not uses the actual the sine, cosine, the constant one. Okay, so it depends on the application and depends on what you what is the problem actually at hand. Okay, but both of them are very common. But I myself, I usually when I train a model, I prefer to have the constant one, because I don't want to put more burden on the model and increase the number of trainable parameters, because that basically increases the number of trainable parameters. And one very important thing that determines whether you want to use a constant or a trainable one, when you know that the maximum length of your sequence is you have a max length of sequence, and you know that you won't have larger sequences larger than a specific length, you can use trainable positional encoding. However, if you have varying sequence length, it's better to use constant positional encodings. Why? Because it can generalize the unseen length of sequences, right? Because it uses a systematic way of representing the position for the patches or for the tokens.
Yes, it makes a lot of sense. Thank you. So we have a question on the chat from Christina. What would you say is the optimal number of trainable parameters?
So the optimal, so one cannot say what is optimal number of trainable parameters. Why? Because it depends on the number of samples that you have and the complexity of the problem. Okay, so one important theory and basically thing that we have in machine learning overall is the Occam-Razor principle. Occam-Razor principle basically states that when you can achieve a task with a reasonable performance, use the least number of parameters that possible. Use the least model complexity. Okay, so if you, for instance, if you have an SVM model, SVM based model, an ordinary model that works with 80 accuracy, the accuracy of 80, and you, for instance, you have a deep learning system that has maybe 10 times of the parameters of that SVM, and it also provides an accuracy of 80, it's better to go with the SVM. Okay, so if for instance, if the positional encoding, the constant positional encoding is providing the same accuracy or same performance as, for instance, trainable positional encoding, it's better to go with the less number of parameters. So it all depends on the complexity of the problem and number of samples, right? Because sometimes, because the problem is so complex that you need to, for instance, make your network deeper, you need to introduce more parameters to your problem to better capture the dynamics of the governing dynamics, because any problem has a governing dynamics.
As a follow-up question, Parsa, let's say you start like a new problem right now, and you need to like implement a model.
Yeah.
What's your first go-to? Do you take like a pre-trained model, or because like you say, maybe some problems are way simpler, so maybe it's not worth it to use like a pre-trained model that has like a huge number of parameters? Like, do you recode the architecture?
So the main thing that one needs to do in machine learning research, and when they are implementing a machine learning model, is to obtain a baseline. Okay, always we need to obtain a baseline for our problem. For instance, a baseline for language processing models maybe 5 years ago was to basically use a TF-IDF. So TF-IDF is a method for representing documents, or what we consider a document, a document unit. For instance, a sentence can be a document, or even a book can be a document, or a page or paragraph can be a document. Nevertheless, TF-IDF is a way to obtain a vector representation for documents. Okay, so until 5 years ago, the baseline was to obtain a TF-IDF vector, a set of TF-IDF vectors, give it to an SVM, and then classify for our problem. Okay, that was the baseline. Right now, for instance, the baseline for a language processing setting would be, for instance, what I introduced in the previous session. To have a pre-trained word, a set of word embeddings, it is very much different compared to a pre-trained language model. Okay, because a pre-trained language model has many more parameters. So to start with a base system, a baseline system, and then see, do you have a reasonable performance on this or not? Then deploy your model, test it on different holdout test set, measure the performance, and then see, and then gradually make your model more complex. Add, for instance, a pre-trained model, or on top of a pre-trained model, add more learnable parameters, because on top of a pre-trained model is an ordinary PyTorch layer. And you can use it as an ordinary PyTorch layer and add more trainable layers on top of it, and have more representation learning. So start from a baseline and then make your model more complicated.
Thank you so much, Parsa. I think that's really good advice for all of our participants, and that's not only related to like natural language processing, like for any problems, as I mentioned. Yeah.
No, I have a bias on NLP because I'm coming from an NLP background.
So we have a lot of thank yous on the chat, but I don't see a raised hand or a question. Maybe I'm going to ask a last one for you, Parsa.
Yes, sure.
So you mentioned in the presentation that the query and value and key, they have like a specific size, like let's say a specific number of rows for the query. Like, is it some sort of parameters you sometimes tweak to play around and see if you get better results, or is it always like the same exact structure? Like, for example,
no. Like, for instance, here, one thing that for in this setting, for instance, here because this product needs to be compatible. This matrix multiplication. Okay, so. When we are using a W of Q to project this X to another space. So for instance, we can project this X to, if these rows in X are in 100 dimensions, we can project to a 10,000 dimensions. Okay. Mm-hmm. And then, but we also need to project this X to 10,000 dimensions. So this query size and key size should be the same. Okay. However, so this also introduces more learning parameters and the number of trainable parameters here. Okay, so we can tweak with these. We can change the query size and the key size. Also, we can change the representation and the value size that we have here. But the value size can be chosen agnostic of what we chose for this. Okay, for key and value. However, if we want to keep the output representation in the same space as what we had in the input space, the value size should be the same as what we have for these rows in the X's. Okay, so it's very common that in the actual, for instance, BERT implementation, they're keeping these representation in the same space. Okay. So because there are many nonlinearities involved in these settings that you really by changing these dimensions, for instance, from 100 to 120, it really doesn't make a difference at the end. Okay, it is the dynamic and the nonlinearities involved in this architecture that make a difference.
Okay, thank you so much. And
I hope I could have contributed something to and made the participant more interested in this topic.
Of course you did, and also you provided them with like great resources. So please all feel free to come back to resources that Dr. Bagherzadeh prepared for you, like the notebook, play around with it, and also the lecture. I know it's like heavy content and it's very technical, but like take time to go through it again if you need to. And there will be a tutorial session next Thursday at 1 p.m. Correct me, Hossein, if I'm wrong. And so if you have questions, you can prepare them for this tutorial, or you can actually post them on the Discord, and the mentors and instructor will do their best to answer them. So thank you very much, Dr. Bagherzadeh, for your time on a Sunday morning, and also for all the effort you put into this presentation. And I wish you all a great Sunday.
Have a good weekend. Bye.
Have a great day, everyone.